All right, moving along with our investigation of determinants, let's look at properties of determinants of matrices. Now I'm going to mention these theorems without really proving them. I think that some of them I'll discuss a little bit, and you can see that they're quite reasonable. First is determinant with zero row or column. If A is a square matrix with a row where every entry is zero. All right, now emphasize that determinants are only defined for square matrices. I don't know if I really made that point strongly enough, but determinants are only defined for square matrices. Okay, so let me start that again. Suppose A is a square matrix with a row where every entry is zero, or a column where every entry is zero. Then the determinant is zero. Now, so what's he talking about here? If there is a matrix here and one of the rows, it doesn't have to be all of them, but if just one of them has all zeros in it, then the determinant of the entire matrix is zero. And the way you prove that is simply row expand along that zero row. Then all the terms in the row expansion will be zero. Or for a zero column, if you have a matrix where one column has all zeros, I could column expand along that zero column, and all the terms in my column expansion would be zero. So that means the determinant must be zero. As we mentioned, to compute the determinant, you can expand on any row or any column that you choose. All right, now we're going to relate determinant to row operations. Okay. Now, suppose we take a matrix and we swap two rows. That's one of the elementary row operations. Okay, it turns out that when you swap two rows, the determinant becomes a negative. You can kind of see that in a 2 by 2 matrix. If I have, say, 1, 2, 3, 4, and I took the determinant of that, that would be 4 minus 6, that would be minus 2. Now if I swap two rows, that would be 3, 4, 1, 2. And that would give me 6 minus 4, which is 2. Now it's quite interesting that the numbers are quite different when you do the computation, but the computation works out to be the same. Okay, so when you switch the two rows, you get the negative of the determinant. Turns out that that's true in general. All right, another theorem that's easier to prove. Suppose you have a square matrix, and let B be the square matrix obtained from A by multiplying a single row. That's another row operation. If I take a matrix A, and I take alpha times row I, okay, that's a row operation, and that gives me a new matrix B. Everything's going to be the same except for the ith row. And it turns out that the determinant of that matrix B is going to be alpha times the determinant of A. Okay, so if I multiply a single row, not all the entries, but a single row, if I multiply a single row of A by the constant I, that will multiply the entire determinant by alpha. And the way you can prove that is simply row expand on row I. Then every term will be multiplied by alpha, which means the entire determinant is multiplied by alpha. Okay, here's another theorem that's going to help. If A is a square matrix with two equal rows or two equal columns, then the determinant is equal to 0. Okay, this is quite an interesting theorem. This follows from the earlier theorem that says if you swap two rows, you change the sign of the determinant. Okay, so if I have two equal rows and swap them, I get the same matrix. But according to that theorem, the determinant has become negative. Okay, so that means the only way that's possible is if the determinant is 0. Okay, so let me just write that again. Here, if I have a matrix and I swap two rows, that should give me another matrix, and the determinant of this should be equal to minus the determinant of this, but they turn out to be the same matrix. The only way for a number to be equal to its negative is if the number is 0. Okay. All right, now we've talked about two row operations. We've talked about row swapping or column swapping. We've talked about multiplying row or column by a constant multiple. Now we talk about the third type of row operation, which is adding a multiple of one row to another row. Okay, adding a multiple of one row to another row. That was the row operation that we used most often, and it turns out that that does not change the determinant at all. It makes no change in the determinant. All right, let's do a simple example. Suppose I have this matrix. I'll just take the identity matrix here. And if I take R1 plus 3 times R2, then that's going to give me 1, 3, 0, 1. Okay. The determinant of this identity matrix is 1. Determinant of this matrix is also 1. Quite incredible. Let's do another example. Let's do 1, 2, 3, 4. And let's take R2 minus 3 R1. Okay. If we do that, we're going to have 1, 2. Then R2 minus 3 R1 gives me 0. 4 minus 3 times 2 is minus 2. Okay. All right, so what was the determinant of this one? It was 4 minus 6 or minus 2. What's the determinant of this one? Minus 2 minus 0 is minus 2. The determinant has not changed under this row operation. So again, I'm not going to prove this. A lot of index stuff. I just want you to appreciate that that's true. All right, so let's do an example now. We'll use row operations to find the determinant of a 4 by 4 matrix. So let's start with this 4 by 4 matrix here. And what's going on here is he's actually doing two things in parallel. He's changing the matrix, and he's relating the new matrix determinant to the original matrix determinant. Okay, so let's see how this works out. So from A, we exchange two rows to get A1. All right, now what does that mean? That means the determinant of A1 is negative the determinant of A. Okay? All right, now, here we perform this row operation where you take minus 2 times row 1 plus row 2. According to what we've seen already, this type of row operation does not change the determinant. Okay? So the determinant of this A2 is equal to the determinant of A1. So that means that the determinant of A is still minus determinant of A2. Okay? This row operation also does not change the determinant. So since the determinant of A3 is equal to the determinant of A2, the determinant of this matrix is still minus, the determinant of A is still minus the determinant of this matrix. Let's go up here. Okay, this row operation and this row operation also do not change the determinant. And you can see these row operations have been chosen so as to zero out the first column. This is the usual way that we do row reduction. Okay, now this one's a little bit different. What this says is that that when you do this row operation, you multiply the determinant of this matrix, let me call this B, is equal to minus 1/2 times the determinant of the previous matrix. Okay? So I should say determinant of A6 is equal to minus 1/2 times the determinant of A5. Now remember, minus determinant of A5 is the original determinant. So in order to get the determinant of the original matrix, I would have to multiply the determinant of this matrix by 2. Okay, so I'm going backwards here. When I compute this determinant, the determinant of this new matrix is minus 1/2 times the determinant of the previous matrix. So to get back to the original determinant, I'm going to have to multiply this new determinant by minus 2, and this minus 2 by minus 1 gives me 2. Right now, when you do these row operations, you still don't change the determinant at all. Actually, the best way to do this is always use this type of row operation where you add a row, a multiple of a row to another row. Then you don't have to worry about this factor. Now here finally, in this last place here, we multiplied by 1/55. That means to recover the original determinant again, we have to multiply by an additional factor of 55. Okay. So what we have here is a row reduced matrix. It's not a reduced row echelon, but it's reduced enough so that we could solve it if we needed to. But the point is that this is now upper triangular. And we saw already that the determinant of an upper triangular matrix is the product of the diagonal entries. So the determinant of this So the determinant of A12 is 1. So to get back to the original determinant, I'd have to do multiply by minus 110. Now, if you're confused by these factors, what you can do is just write down your row reduction and then go backwards. This 1 over 55 means I need to take the final result, which is 1, multiply by 55. This doesn't change, this doesn't change, this doesn't change, this doesn't change, this doesn't change. Here I'm going to have to multiply that by minus 2. Doesn't change, doesn't change, doesn't change, doesn't change, doesn't. And this one I'll have to multiply by minus 1. So this is a minus 1 factor. This is a minus 2 factor. And this is a 55 factor. Okay, and so that will get you what you need. Now, did I miss something here? Oh, here, sorry, I missed another minus 1 factor. This is a minus 1 factor also. Whoops. Whoops, this is a minus 1 factor here. So 55 times minus 1 times minus 2 times minus 1. All right, so if you don't understand this example, you can watch through it again. I'm sure it's hard to catch on the first time. And hopefully we'll do some more examples of that as well. All right, so I'm going to stop here.